Welcome back to the Global AI Student Conference, and we're here almost ready to welcome our next speaker, Sahan Disanyaka, which I completely mispronounced that name, but they are a Gold Microsoft Learn Student Ambassador who will present to us about a hybrid model approach for real-time acoustic anomaly detection using time series. Sahan, hello!
Hello, hope I'm well audible.
Thank you, and how are you doing today?
Yeah, I'm feeling awesome, and I heard Feral session went on Global Student Summit 2022, so it's feel awesome.
Awesome. Well, we're super looking forward to your talk. So feel free to start sharing your screen and take it away.
Yeah, thanks so much. Okay, let me share my screen. Hope my screen is visible to you.
Yes, we can see your screen.
Okay. So, hi guys, good morning, good afternoon, good evening to everyone from wherever you are joining to Global AI Student Conference. Hope you all are enjoying Global AI Student Conference so far. So the talk I'm going to deliver today is hybrid model approach for real-time acoustic anomaly detection for machine condition monitoring. First, I must extend my regards to my supervisor, Dr. Manjushri Vikramasinghe, and also my co-supervisor, Mr. Pasinu Marasinghe, on this occasion. So this is a research project which currently moving ahead, and also currently I am working on it. And I hope it will be very interesting for you for listening this research project. And I hope many of you have many suggestions. I would like to take this as in our Q&A session. So talking about myself, I'm Sahan Disanaika. I'm a Goals Microsoft Learn Student Ambassador and also final year computer science undergraduate at University of Colombo School of Computing. And also I'm a GSOCA in 2021 at Scholar organization. So let's first analyze what is the outline for today. So first, we will discover the background and the challenge of real-time acoustic anomaly detection, and then the methodology and datasets and the baseline, then accordingly feature extraction and modeling, and then finally, let's look at a small demo. So it is crucial to discover the background behind the research to build a foundational understanding about the research problem. So let me ask you a quick question and blow your mind a bit. A machine, and can a machine hear if a machine is broken? So, okay, so think, can a person, an expert technician, hear a machine is broken? So the answer for the second question is obviously yes. An expert car technician, a motor technician can identify an anomalous behavior of a machine. So what about the first example? Can a machine hear a machine is broken? So this is the question that we have. The best example I can give you is during my first year, 3 years back, me and my fellow colleagues went on a trip to Kandy, one of the main cities in Sri Lanka, by train during our vacation. So we started off in Colombo railway station. So half of a journey, an old man, later we got to know he's a usual passenger in the train, near us, told that the train is not going to make it for Kandy because the engine sound is not good for him. So we didn't took that much serious, but however, the train has to stop before reaching to Kandy due to a engine breakdown, and we had to wait around 2 to 3 hours until a new engine replaced with the current engine. So as a computer science student, I got a question. What we can't replace this human expertise for identifying anomalies with trained model with the help of machine learning? and learning and identifying anomalies as early as possible to avoid such difficulties. Maybe it's a very small problem at the early stage of the analysis, but at the end it has become more complex problem to solve. So that becomes the motivation to my study. So if we are to build such computerized method to detect anomalies, we need to map the real world human behavior into a machine learning. That is how science evolved, by taking human behaviors into consideration. So I have uh, discovered three major considerations. First, the human. In our example, the old man had previous experience on anomaly situation, but if we are to perceive that uh, if we are to perceive that the machine learning model has to have good knowledge, and we need a sophisticated data set with us. And second, he is well trained to identify anomalies. For that, the above mentioned model, we need to train it properly with using machine learning and deep learning models to detect anomalies. And last, human has correctly predicted the anomaly behavior. It's not a false positive. So it has a high accuracy and give remedies early. So our model, to be accurate, it needs higher accuracy and also be proactive measuring anomalies. So the challenge here is how to deliver a proactive model for detecting acoustic anomalies at real time. So this problem, the real-time acoustic anomaly detection, can be considered as a special case of anomaly detection, since we are using acoustic data for analysis purpose and also detecting at real time. This problem comes under the time series domain, since we analyze acoustic data. So how it becomes acoustic data into time series data? So the formal definition for time series data is the any observation that has recorded measurements in the orderly fashion and correlated in time dimension creates a time series. So that definition well agrees with the acoustic data, since it made out with the variations of amplitude and frequency properties with the time. So the above figure show a clear picture how time series and acoustic data are related to with each other. And when it comes to anomaly detection, it can be defined as a process of identifying data points which are deviates from its dataset's normal behavior. So as an example, the current economic situation around the globe is an anomaly with respect to the normal behavior and the past economic behaviors of the world economy. So the anomaly in different sources has mentioned as in different names as outliers, as novelty points, but it all carries the same semantics. But if we dive deep in and also concerning about anomaly data, there are several types, but there are on it's fair to say there are three major types, namely the point anomaly. It refers when a single observation deviates from the other observation. A good example is a sudden gunshot in a quiet environment is an example for point anomaly. And then secondly, collective anomaly, a sudden few gunshots in a quiet environment is a collective anomaly. And thirdly, the contextual anomaly. Consider the gunshot happened at Ukraine may be may not be an anomaly, since in a situation like those people heard gunshots infrequently, but a different country like Sri Lanka, maybe in your country, the gunshots may be an anomaly. So is anomaly detection that much hard activity? So sadly, yes. So owing to the facts of the of I have mentioned in this slide. So you may have argued with me, it's we can do a simple binary classification problem for anomaly detection if we have label data for normal behaviors and also for anomaly behaviors. Yes, obviously yes, but the thing is the normal behavior is evolved with time. So in many fields, including machine condition monitoring, the normal behavior has evolved with time. The one good example is the COVID virus. In 2020, it has only one variant, but gradually it has improved its behaviors and it creates more and more variants. So that's how it changes its normal behavior. And also the problem of domain generalization. Consider an example if we have a machine built in USA and we are deploying that same machine in Sri Lanka or India or China or Australia. So it has different environmental conditions. So if we have to build a domain generalizable property included model, it has to address those different domain generalization properties for different environmental conditions. And lastly, the unknownness of anomalies. Until anomalies happen, we don't know if it is an anomaly or not. So these are the most complex things, and also we can name it as challenges in anomaly detection. So with the improvement of the computing power and the big data, it made possible to do anomaly detection at real time. Under real-time detection, it has many advantages, namely, it helps identifying issues and take actions immediately. Information is up to date and can be used immediately. But in our case, it's not strictly real time, but it has taken a few time to do the data processing part. But again, it's really useful to have information is up to date, and delay in data processing is minimal compared to offline training. So the best example is the radar map. Hope you all know about radar. So it's a really good example for real-time detection. And when we carry the detection at real time, technically it has some differences compared to the typical acoustic anomaly detection in offline training at acoustic data. So the major four differences uh, we can do when we are building a high-level architecture for real-time acoustic anomaly detection task, I have discovered four major differences between offline trained model and the real-time acoustic anomaly detection. So the thing is, at offline mode, so we don't need additional configuration for noise cancellation and explicitly defined dataset for both training and the inference task. And also the build model at the training phase are we straightforwardly used for the inference task. And also we predict normal and anomaly behaviors at offline mode. But at real time, the difference is we need a raw audio form and raw audio source for the inference purposes. And also we need additional configuration for noise cancellation, and it needs a pre-trained model. And obviously, yes, we predict anomaly behaviors at the real time. So if we map those differences into an architectural perspective, so this is how it looks like. So in offline based model, we have uh, explicit training data set, and we train it offline mode, and we doing inference at the offline mode. But at the real time, we have a raw audio form, and we do necessary configuration for noise cancellation, and we did offline. We have a pre-trained model, and we do the real-time inference task. So this area is highly commercial valuation, has a high commercial valuation and many useful application, namely machine condition monitoring in industrial application, intrusion detection systems, surveillance systems and network application, military application, in deployed military vehicles, medical applications, detecting bird noises, music instrument failure detections are many, and there are many examples I can give you for this real-time acoustic anomaly detection. So in here, we are only focusing on machine condition monitoring. Let's talk it as MCM. So we only consider in this domain. So moving ahead about the literature perspective of our research project. So and the area of the acoustic anomaly detection is still underrepresented, and not many research plays due to the fact that lack of publicly available datasets. That is the major reason, but it is an active research area for several years from 2014 to 2022. And you can find around 50 research papers by now under these keywords in open access archives for the same name called real-time acoustic anomaly detection. So the contribution from our study, we hope it may be vital for the whole research community. And since we are much interested in the model approach, let's dive into it. So mentioning about the related models, there are mainly four model categories. The first time is traditional machine learning models. The classical machine learning models are the earliest. in the model classes. The early studies employs support machines, Gaussian mixer models, hidden Markov chain models. But nowadays, those classical models are used as a candidate models for building the hybrid models. And the most widely used model category is autoencoder based model for acoustic anomaly detection. Those also there are established many variants on the autoencoder models like uh, dense autoencoders, variation autoencoders, denoising autoencoders. Might you can come up with your own architecture for autoencoders. There are a lot more. So and also the other two categories are the CNN-based models and the row-based signal models. Talking about the row signal-based models, since these are the models uh, recently came up with the wavenets and hierarchical temporal-based models, usually using uh, for time series classification and generation parts. So talking uh, about the models, you may have observed that I frequently use the hybrid models. So what's the reason behind that claim? So there are two main evidences I can give you. What's the reason behind the recent surge of hybrid models in research domain? The first one is the forecasting competition, time series forecasting competition results and time series challenges and recent publications. So the major finding is the M4 competition results. The Macridas et al. Is one of the uh, main researcher in time series forecasting, mentioned that the hybrid models are the next breakthrough in time series forecasting, and also it same applies for the time series anomaly detection as well. And the second example is the decade challenge results, which is predominantly focused on time series anomaly detection for acoustic data, and hybrid model performed by proposed by Siamese Corporation won the decade 20 challenge, which ended recently. So talking about the learning techniques, uh, the supervised model is one of the earliest learning techniques. It needs pre-labeled normal and abnormal data, but later researchers have moved for unsupervised learning and self-supervised learning, and recently for future learning. But the most researchers have are still at the unsupervised learning at the self-supervised learning. The self-supervised learning is some variant of unsupervised learning. It needs some sort of training data and also unlabeled data. And talking about the available data sets, for our research at the earlier stage, we could find a few publicly available data sets. The most popular one is MIMI data sets, MIMI, and there are few variants of it. And also you can find less popular data sets like DMT, ISA electrical engine data sets. So those are the candidate data sets for our project, but we chosen that MIMI data sets for our research activities. And let's dive into the methodology. So how we are build our real-time acoustic anomaly detection system. So we propose our own pipeline to exhibit the main component for building a real-time acoustic anomaly detection system. It has 4 components. So let's analyze each phase one by one. As you may have observed, the earlier architectural diagram I have presented to differentiate the real-time acoustic anomaly detection and the offline acoustic anomaly detection. So it same applies for here as well. So in the offline training model, the main purpose is to train a pre-trained model, to take a pre-trained model. And at the real-time inference phase, we observe the streaming data from the raw uh, audio waveform, and from the pre-trained model characteristics, we are predicting that the incoming data, how much anomalize for the incoming anomalies data. So if we dive into one step deeper, the low-level acoustic features, uh, how the low-level acoustic features convert into analyzing anomalies given by this diagram. So if I elaborated more, the raw audio waveform converted into a spectrogram at the feature extraction phase, and our model approach, hybrid model to be exact, So analyzes and extracted features, and then our anomaly score model analyzes and assign an anomaly score based on the deviation of its from its normal behavior. For now, we have incorporated two candidate models for our baseline model task. First, a dense autoencoder and a mobile VNet model, CNN model. And then we created a simple hybrid model for combining those two architectures in such a way for building a convolutional autoencoder. So for the data integration, for the offline offline training purposes, we incorporated Mimi and MimiDev datasets since it has advanced labeling and it has additional configurations for present for domain shifted conditions, and it's really help for us to address the main problems in anomaly detection. And also for the raw audio signal source at the real-time inference phase, we integrate additional noise cancellation and pre-processing mechanism, including with the denoising layer. And to talk about more about MIMI datasets, it's abbreviated for malfunction in industrial machine investigation and inspection. It made available by Hitachi Limited under Creative Commons license, and there are four machine parts, namely valve, pump, fan, and rail slide, and it has around 1,000 normal instances for each machine type, around 150 instances for each abnormal instances, and it downsampled for 16 kilohertz. These are additional configurations for about datasets. And let's jump up to the feature extraction phase. So feature extraction, as you know, it's a process of highlighting the most discriminating and the most impactful features of the acoustic signal. And then we use windowing technique to remove the spectral leakage, to analyze the series with more ease and divide it to small segments. It's really easy to partition into small number of segments and processing it. So this is the most popular widely used windowing equation for to take the number of segments in a acoustic signal. So same step size and the window length use of both offline and real-time audio inference. So windowing results a feature map, as you can see here. So the audio features, we converted it into a time domain from the frequency domain. Since it move into a frequency domain, it enables to capture more wide range of features. So it can be enabled to taking by the Mel spectrogram by defining a hop length and a frame size, as you can see in those two diagrams. So these are some of the results we have taken from the feature extraction phase. The most effective method is the log-mel spectrogram, as we have analyzed in our experimental phases. So if I elaborate more, the spectrogram obtained from the Fourier transformation is a 2D representation, and we feed those spectrogram sequences into the model as feature vectors. And then as the most important phase of our pipeline is the modeling and the training part. So we incorporated three major model classes to form the hybrid models. By now, we only incorporated autoencoders and CNN architectures, but later phases we are hoping to integrate GAN models with LSTM models. So the hybrid architecture attempts to improve the model's performance by aggregating its model capabilities, we are forming a novel architecture. So having a special concentration on the reconstruction based model. So it is kind of a separate model class of the whole acoustic anomaly detection model classes. So the namely autoencoders, which are very useful for detecting point anomalies and collective anomalies. So, and also the CN architectures are very effective for analyzing the collective anomalies, but less effective on detecting the contextual anomalies. But so our initial hypothesis was by incorporating and building a hybrid architecture will address uh, more proactive model, will result a proactive model to detecting both three anomaly types, namely point, collective, and contextual. And since the feature extraction generate the set of spectrogram, so the modeling phase are detecting and training the learning the spectral features detected at the feature extraction phase. So this is the network structure of the baseline AE model. So as you can see in the right hand side, this is a keras implementation of our dense autoencoder model. So there are 4 layers for encoder and decoder, and then we come up with Lockmel energy of 128 beans, and we incorporated batch normalization with a relative activation date. And this is the network layer uh, diagram for our dense autoencoder architecture. As I said, there are 4 layers for encoder and also for the decoder, and it has late 8 neural network for the latent space. So these are some of the experimental results we have obtained for the training loss for both for main 4 machine types, namely fan, slider, pump, and the slave slider. So the hybrid model approach, which we have implemented by integrating the CNN architecture and the auto encoder model. So this is the spectral features and the network architecture are pretty much similar compared to autoencoder, dense autoencoder, and also you can see the keras implementation of the convolution autoencoder based model we have implemented. But as a quick note, this is some kind of an improved version of the Ribeiro et al. 2020 proposed model, but the very less models have been implemented for real-time acoustic anomaly detection, not for offline training purposes. So this is the network layout for the convolution autoencoder architecture. As you can see, uh, it has a shape of a convolutional neural network with a latent space of the autoencoder. The results we have obtained from the convolutional autoencoder are pretty much same as the autoencoder, but it has very improved results. And talking about the last phase of our pipeline, which is the anomaly score calculation, it is where it analyzes the how much the obtained signal is
Hey,
deviated from
Sahan,
its normal behavior.
you're doing great, but you've only got like 2 minutes left.
Okay, thank you. So the total reconstruction error given by the summation of mean distance for all sequences. And this is the most widely used evaluation matrices we have already integrated for RUC and also the partial AUC as our evaluation matrices. And this is the most important part where we are integrating the anomaly score calculation, where we calculating the error between the reconstruction based signal and the normal behavior of the signal. So based on that, we are taking an anomaly score, and based on the threshold we are defining at by the Jordan index, which is denoted by J, we are indicating that the anomaly score, whether the signal is anomaly or a normal signal. And at last, since I have a limited time up left, so it is the results I have taken for the dense autoencoder and for the hybrid models. As you can see, it has more improved behavior with respect to the dense autoencoder. And as you can see, it has more the dense autoencoder is pretty much good for analyzing anomalies, but not for the detecting the normal behaviors. As you can see, recall is at 1.0 and precision is at 50%. But in our hybrid model approach, it has 72% of precision and 83% of recall. So technology and software is pretty much a Python-based implementation. And let's dive into a quick demonstration. Let me wait to open my code faces. And yes, this is my React frontend application, which have deliberately to implement the auto to analyze the real-time acoustics. So this is somewhat a proof of concept model. So to currently it has predicting that a model is under the 36 model, but later we'll see in quite a while the anomaly score will change gradually. Now it's 18.81, and it will see since it take some time to do the pre-processing task for the detection of the anomaly score. So that's all I have to present you today. Hope you all enjoy my presentation. So thank you very much. Thank you, Global AI Student Conference, uh, the whole organizing team for giving me this valuable opportunity, the wonderful opportunity to present about my research project. Thank you.
Yeah, thank you.